There are different sizes of infinity. Not metaphorically, not philosophically, mathematically, provably, some infinities are bigger than others. And if that didn't break your brain a little, let me say it again. The infinity of whole numbers, 1, 2, 3, 4, going on forever, is smaller than the infinity of decimal numbers. They are both infinite. One is genuinely, measurably larger. A mathematician named Georg Cantor proved this in 1891 with a single diagonal line, and it was so controversial that the math community tried to destroy him for it. Here's what your brain does when it hears the word infinity. It imagines the biggest thing, the end of all ends. And if there's one infinity, the biggest thing, then there can't be anything bigger, right? That's what infinite means. Here's what's weird. That intuition is wrong. Not wrong like slightly off. Wrong like your brain built a model of infinity that doesn't match what infinity actually is. To understand why, we need to ask something you've never been asked before. What does it actually mean for two things to be the same size? Not count them, because you can't count infinite sets. That's the whole problem. Here's the trick Cantor used. Two sets are the same size if you compare every element of one with exactly one element of the other. No leftovers, no doubling up. Like chairs and people at a dinner party. You don't count, you just check. Is everyone seated? Any empty chairs? This is called a bijection, and it's the key to everything. Same size test. Can you pair the two sets perfectly? Let's start somewhere surprising. How many even numbers are there? Half as many as whole numbers, right? 1 for every 2. So the evens should be a smaller infinity. But watch. Every whole number pairs with its double. 1 goes with 2, 2 goes with 4, 3 goes with 6, forever. No number left unpaired on either side. By our same size test, they're the same size. Your brain hates this. Mine did too. But the math is clean. The counting numbers, the integers, even all the fractions, same size. Mathematicians call it Aleph Null, the first infinity. Now, here's where it breaks. What about the real numbers? Every decimal, every point between 0 and 1. Not just the nice ones. Every infinite, non-repeating decimal. The square roots, the pies, the numbers that go on forever with no pattern. Cantor asked, can you pair these with the whole numbers? Is there a bijection? Suppose someone gives you a list. They claim it contains every real number between 0 and 1. Row 1 is the first. Row 2 is the second. On forever. Cantor says, I will find a number that isn't on it. Take the first digit of the first number, the second digit of the second, the third digit of the third, the diagonal. Now build a new number. Change each diagonal digit. If it's a 4, write a 5. Anything different, just not the same. This number differs from row 1 in the first digit, row 2 in the second, row 3 in the third. It differs from every row, at exactly the position we used. Your list claimed every real number, but this one isn't on it, which means no such list can exist. You cannot pair the reals with the whole numbers. The real numbers are a strictly larger infinity. And this isn't just two sizes, it's an infinite ladder. You can always take any infinity and construct a larger one by taking every possible collection of its elements. Every time you get something strictly bigger. Aleph Null, Aleph 1, Aleph 2, infinitely many infinities, each larger than the last, forever. Cantor asked, is there an infinity between Aleph Null and Aleph 1? He believed the answer was no, called it the Continuum Hypothesis, spent the rest of his life trying to prove it. He couldn't. In 1963, Paul Cohen proved why. It's independent of mathematics. You can build math where it's true, math where it's false, both valid. The math community called him a corrupter of youth. He died in a sanatorium in 1918. But Cantor didn't just prove some infinities are bigger. He proved our intuition about size, the thing we use every day, completely breaks down at infinity. And the only tool that still works? Match things up 1 to 1. Ask, is anyone left standing? That one idea, that one diagonal line, cracked open mathematics and never closed again. Not even close.